Okay, now we're going through some ideas of switching between geometric ideas and matrix ideas. So here's our first example is part activity 263 part A. Find the matrix of the transformation that has no effect on vectors, that is t of x equals x. So then t of e1 is going to equal e1, t of e2 equals e2. So the first column is then e1, the second column is e2. So there you go, it's the identity matrix. So for part B, find the matrix of the transformation that reflects vectors in R2 across the line y equals x. So then I drew y equals x as this kind of orangish yellow line, and then I drew E1 and E2, and then in a different color, I wrote where does E1 get sent? Well, T of E1 and E2 get flipped. So E2 is E of E1, so you put E2 there. So there's E2 in the first column, and then where does E2 get sent? It gets sent to E1. So then you put E1 there, and that gives us that matrix 0, 1, 1, 0 for that matrix transformation. What is the result of composing the reflection you found in the previous part with itself? What is the effect of reflecting across the line y equals x and then reflecting across the line again? Provide a geometric explanation for the result as well as an algebraic one obtaining by multiplying matrices. So geometrically, here's the line y equals x. You flip over, flip back, you're back to where you started. So it should be the identity. And look, when I multiply this matrix times that matrix, then row, column, you get a 1, row, column, you get a 0, row, column, you get a 0, and bottom row, right column, you get 1. And so that is the identity matrix and matches with being the identity function. Okay, now let's find the matrix that rotates vectors counterclockwise in the plane by 90 degrees. So now E1 goes up to where E2 is, and E2 goes to a negative E1. So since E1 goes to E2, you put an E2 there. And so then since E2 goes to negative E1, you put a negative E1 there. And that gives you that matrix 0, negative 1, 1, 0. Now for part E, compare the result of rotating by 90 degrees and then reflecting the line y equals x to the result of first reflecting in y equals x and then rotating 90 degrees. So here I'm going to go down, and then this is going to be the first one. So this is first. And then this is second. Okay. So the first example is you start off with E1, E2. And then you flip them over the line y equals x. First we rotated 90 degrees. So we rotated 90 degrees. So then E1 is where E2 was, and E2 is where negative E1 is. And then we reflect over y equals x. And so E1 gets reflected. Its reflection is right there. E2's reflection is going to be right there. So then you've got E1 there and E2 there. And that matches when we do matrix multiplication. Remember, this is the 90 degrees. This is the y equals x reflection from above. So notice that the one I'm doing first is on the right because the matrices are kind of like functions. And so the one closest to the variable is the one you're doing first. And so then multiplying those together, you get 1, 0, 0, negative 1, which matches E1 going to itself, E2 going to the negative of itself. Now, if I were to, here's the E1 and E2 again. Now, if I flip over y equals x, then they get switched. And then if I rotate 90 degrees, then E1's there and E2's there, which is E1 going to negative of itself would be that, negative 1. E2 staying the same would be, there's E2 again. And this is the one that flips over y equals x from above. This is the one that rotates 90 degrees counterclockwise. And so then combining them, we get negative 1, 0, 0, 1. Notice that these are negatives of each other, and these guys are negatives of each other, which makes sense. Okay, and then part F. Find the matrix that results from composing a 90-degree rotation with itself 4 times. That is, if T is the matrix transformation that rotates vectors by 90 degrees, find the matrix of T for T composed with T composed with T composed with T. Okay, so explain why the result makes sense geometrically. So geometrically, if you do 90 degrees 4 times, you've gone 360 degrees. And 360 degrees is the same as doing nothing. So then it should be the identity function. Then that makes sense because now if I have t 4 times, I divide it up into 2 of them. So then multiplying those together, I get -1, -1. And since it's the same thing over here, it's -1, 0, 0, -1. And then multiplying those together, you get 1, 0, 0, 1, which is the identity. So geometrically, it should be the identity. And then matrix multiplication gives us the identity matrix. So that checks out. And then part G, explain why the matrix that rotates vectors counterclockwise by an angle theta is cosine theta, negative sign, positive sign, cosine. Well, say I start off with the red lines here, and then I rotate it to be the green lines, and I rotate it theta degrees. Then the x component here will be cosine theta, the y component here will be sine theta, but then over here, this angle's from the positive y axis. And so that means that that angle is the same as, I don't know what color I chose there, the same as this angle, which means then that the distance here would be negative sine, because it's the opposite, and it's going in the negative direction, whereas the distance here would be cosine of theta. And so that gives this matrix. So E1 is to cosine sine, E2 gets sent to negative sine cosine, matches up. Okay, and that completes activity 263G.